All right, welcome to today's explainer. If you're out there working with large language models, you already know that the ultimate hurdle isn't just training the things, it's actually getting them ready for real-world deployment. You know, when you're moving from a cozy research environment into actual production, things like size, speed, and latency are absolute deal breakers. Today, we're diving into a really fantastic practical implementation from MarkTech Post that tackles this exact problem head-on. We're going to see how to compress and benchmark instruction-tuned LLMs using a tool called llmcompressor. We'll be navigating those absolutely crucial trade-offs between a model's efficiency and its actual generation quality. Let's get into it.
Okay, so here is our game plan, our deployment journey for today. Number 1, establishing the FP16 baseline. 2, fast and data-free FP8. 3, prepping the calibration dataset. 4, aggressive compression with GPTQ. 5, advanced tactics with SmoothQuant. And 6, the final benchmark showdown.
Section 1. Establishing the FP16 baseline. To get things off the ground in our collab environment, the coding setup is super straightforward, but honestly, it's vital. First up, we install our required libraries and just make sure we have a CUDA-enabled GPU ready to do the heavy lifting. Second, we define our base Qwen 2.5 model in its completely original 16-bit floating point precision. And third, we set up our helper functions. Think of this step kind of like setting up the referee before a big match starts. These scripts are essential for memory cleanup, calculating the actual model size, timing the generation speed, and evaluating perplexity. We have to do this so we have a perfectly reliable starting point to accurately measure exactly what our upcoming compression tactics are actually doing.
Now, throughout this explainer, we're going to be relentlessly tracking these 5 specific practical inference metrics. Why? Well, because deploying an LLM is essentially a constant balancing act between efficiency and accuracy. We'll monitor disk size to see exactly how much VRAM we're saving. We'll check generation latency and throughput to see how fast the model responds and processes tokens. But crucially, and I mean absolutely crucially, we'll also track perplexity. This basically measures how confused the model is, so lower is better here. We'll also monitor overall output quality just to make sure our compressions aren't, completely destroying the model's actual intelligence.
Moving right along to Section 2, Fast and Data-Free, FP8.
The surgical precision of this technique is just fascinating to me. FP8 Dynamic Quantization doesn't just blindly crush the entire model down. Instead, it specifically targets the linear layers, compressing them down to 8-bit precision. But, and here's the really clever part, it leaves the language modeling head in a higher precision state. This selective approach is specifically designed to aggressively shrink the model while actively preserving its generation quality. And even better, it does this dynamically, without needing any external data to figure out how to compress the weights.
Because it literally doesn't require a calibration dataset, this FP8 recipe is incredibly quick to apply. It gives us this immediate, actionable baseline for what a compressed model looks like in practice. Once applied, we just save the compressed model and run our benchmark functions all over again. Right away, we get to see the new compressed disk size, the updated latency and throughput, and how the perplexity holds up against our original FP16 baseline.
All right, let's step it up. Section 3, Prepping the Calibration Dataset.
So when we compare our methods, FP8 is fast and data-free, but GPTQ and SmoothQuant, those are data-driven. If we're really going to squeeze this model down to 4 bits or apply complex smoothing techniques, the algorithm absolutely needs to observe how the model handles realistic inputs. This minimizes errors during the actual compression process. We can't just guess here, we literally have to show it. And that is exactly why we need to pause our compression journey for a second and build a solid calibration dataset.
And here's the quick procedure for prepping that data. First, we gather realistic instruction-style inputs using a small set of UltraChat samples. These are perfect because they mimic a real human talking to the model. Next up, we convert these chat examples into model-compatible text using the tokenizer's specific chat template. Finally, we tokenize these samples with a fixed maximum sequence length. Boom! This creates a highly reusable, incredibly realistic dataset that will act as the crucial foundation for our next 2 aggressive quantization techniques.
Section 4, Aggressive Compression with GPTQ. Let's see what this data lets us do.
This brings us to a really vital question, and you've probably been wondering this yourself. How does aggressive 4-bit weight compression actually affect our perplexity? I mean, we are talking about drastically reducing the disk size of the model by slashing the precision of its weights. But in the real world, a tiny model is totally useless if it starts generating absolute garbage, right? This trade-off between a tiny disk footprint and the model's accuracy is pretty much the primary tension in AI engineering right now.
So enter GPTQ W4A16. This method compresses those linear weights all the way down to a crazy 4-bit precision, but it keeps the activations in higher precision at 16-bit. Think of it kind of like packing a suitcase, right? We're aggressively folding the clothes inside, those are the weights, but we're leaving the hard outer shell, the activations, totally intact to protect everything inside. More importantly, it uses the calibration dataset we literally just built. By observing how data flows through the network, GPTQ mathematically reduces the reconstruction error. It carefully calculates exactly how to pull off this severe 4-bit squeeze while preserving as much of the model's original intelligence and quality as possible.
Moving to Section 5, Advanced Tactics with SmoothQuant. SmoothQuant addresses a very specific quirk in language models, activation outliers. Sometimes certain activations will just spike to extreme values, making them extremely hard to compress accurately. SmoothQuant is this advanced pipeline that mathematically smooths out these outliers across the network before we even apply an 8-bit compression, specifically GPTQ WA8. Actually, by smoothing the math out first, we retain remarkably high generation quality even after the whole model is quantized. It's a really brilliant approach.
And now, Section 6, the final benchmark showdown, the moment of truth.
This table brilliantly illustrates the entire purpose of this exercise. When we look at the final benchmarking code output side by side, the real-world trade-offs are completely laid bare. Just watch how the disk size shrinks dramatically from that heavy FP16 baseline all the way down to the tiny GPTQ W4A16 variant. You can track the latency dropping and the throughput surging as the models get significantly lighter. But keep your eyes locked on that perplexity column. You can see exactly how much accuracy you're sacrificing for that blazing speed and minimal size. FP8 gives you a fast, data-free reduction, while the GPTQ methods achieve much stronger compression, but they rely heavily on that calibration data to fiercely defend the model's accuracy. This quote hits the nail on the head and captures the absolute core takeaway from the source material. What we've explored today isn't just abstract theory. It's a highly practical, ready-to-use workflow. By saving each quantized model and testing its generation quality, this entire setup acts as a bridge straight to a real deployment pipeline. You now have the exact framework you need to test these post-training quantization methods yourself right in a Colab environment.
Look, as you design your own inference systems, the choice is never going to be one size fits all. Are you severely memory constrained? Do you need absolute maximum throughput, or is maintaining the highest possible precision your absolute top priority? You've got the tools, you have the methods, and you now have the metrics to figure it all out. So as you head back to your own AI engineering projects, I'll leave you with this final challenge to think about. Which quantization trade-off will you choose for your own real-world deployment? Thanks for joining me on today's Explainer, and happy coding.